Greetings everyone, this is Non-Expert here, back again with another video. Today we are going to be solving the alien dictionary problem, and this problem has been suggested to us by Aditi, and I'm really happy that she told me about this problem because even though I've solved this problem a lot of times, while going through the daily coding problem mailing list, I couldn't find this problem. Maybe the mail got deleted, or maybe my search wasn't extensive enough. And I'm pretty sure there would be variations to this problem inside the daily coding problem mailing list. But overall, it's really absurd that this problem wasn't there because this is one of the more popular problems which have been asked in a lot of interviews. And in the past 1 year, this problem has been asked probably it's one of the more popular questions which have been asked in Google, and this has also been asked in Amazon and in Microsoft. So pretty important problem to know. But today we are not just going to go ahead and just talk about some algorithm before we sort of move forward. We're going to use our basic intuition and then move forward with our solution. I think that approach would be better. And by the end of it, I would be able to tell you like this is the algorithm that you've actually implemented. Cool. So fortunately, we're able to find a similar problem on lint code and not lead code. And although lead code does have the same problem, it has its own premium membership. So if you want to do that, go ahead and get it. But we usually go for the free version. So lint code had a free version on this. Just a word of advice though, lint code is still a work in progress. That's what I believe at least. And there might be a few test cases that might not be working. So it's okay if you get a few test cases which are not working, as long as you understand what's the basic idea behind this entire solution. Cool. Putting all that aside, let's just go through the description of the problem. So there's a new alien language which uses the Latin alphabet. However, the order among the letters are unknown to you. You receive a list of non-empty words from the dictionary where the words are sorted lexicographically by the rules of this new language. And we need to derive the order of the letters in this language. We're given a few assumptions over here. You can pause this video and check it out in the link given in the description below, or just pause this video and check out over here. But just to iterate one more time, you can imagine this as a scenario that there's a new language that you don't know the ordering to. You do understand the alphabets which are coming in, but you don't know how they are structured, how they are ordered. So for us, we know for a fact that inside our dictionary, it's always going to be from A to Z. A being given the precedence over here, and then Z comes at the very end. So if you have something like Apple, that will come way before you get to zoo or something, right? So using the same logic, we are going to build out an intuition on how we can understand what's the ordering behind this particular dictionary which we have. And inside the input, we have a list of words, which is basically a list of words inside the alien dictionary, and we need to understand what's the ordering. So if we go, and how we usually go inside dictionaries as well, if we check items in pairs of two, you can look at this particular pair, which is WRT and WRF. When we look at this, we understand that even though WR, the two characters are the same, the next character, which is the third character, is not the same. So we have T and we have F, and by that we can say that T should always come before F no matter what. So you can see that in the output that's the case as well. So our intuition over there is right. So let's check the next pair, which is WRF and ER. Over here, the very first characters are not equal to each other. So by that, we can say that W should always come before E. So we have that as well, which W is coming before E. And if you sort of take the next pair, we have ER and E double T as well. So E is same for both the pairs, but R and T are not same, so R should always come before T, and you can see that over here. So we must be asking like, how do we know whether W comes before E, which comes before R, which comes before T, which comes before F? How do we get that intuition out? That's actually one of the more important problems that we need to like worry about. We can't just like say that hey sorry, T is just greater than F, so T and F should like come one after the other. We can't really do that. Um, so if you sort of look at this problem, you can actually draw it out on a piece of paper, and you might see that there is a graph which is getting built out, which would say that, hey, if we look at W, W should come before E, and if you look at R, we know for a fact that R should always come before T, which we deduced from this pairing. And if you look at these two pairs, we can say that E should always come before R. So we can say the W always comes before R, and that's how the entire graph gets built out. So you need to join all those things as well. So that's the basic intuition behind this. Let's just go ahead and open the code so you can see that it's quite similar to lead code. There are just a few things here and there, not that different, but we just have to implement this function out, and that's basically it. Cool. So before we start, we sort of already gained an intuition behind how we're going to be doing the pairings. And while we're doing the pairings, we can see that we need to understand whether W goes to E or R or something or the other, right? So just how we sort of build our graphs, we can do the same thing over here as well. So we're just going to create a variable, call it as graphs, or let's just call it graph since it's just one. And we can just create it as default dictionary, which we usually do. And instead of just having a list, because obviously one node could be pointing to multiple values, as you know, inside a graph, we would use sets instead of a list, just because I don't want to take care of I want this thing to take care of the duplicates on its own. That's one thing out of the way. The second thing is, how do you know whether something comes before? Like, we know that this thing is pointing to something, but how do we know that W comes way before F or something, right? So we already can see that over here. We know that W needs to come before F, but how do we deduce that thing? To do that, we could probably actually use a simple understanding of BFS structures, but also while doing that, we need to maintain an in-degree count. An in-degree count would just help us analyze and understand whether something can be processed or whether something cannot be processed. So if something is at the value of, and actually let's just build this out and I'll just keep on explaining it as I'm going forward. I'm going to make the in-degree variable as a dictionary. It's going to take the character as the key, and the value would be an integer value. And if the value is 0, we would say that this is at a level where it can be processed. That will sort of help us understand what's the idea behind how can we do the next processing as we're moving forward. So let's just do that really quick, and I'm just going to pick up all the values which are there. Inside Python, we have ASCII lowercase, which sort of returns everything. So if I do a quick print over here of the in-degree, we would see that we have values from A to Z with the values as 0 over here. Cool, that thing works. It's awesome. We also need one other thing, and this sort of depends on what the interviewer really wants, which is, what if you have a case where you have AB and AC, and that's it. So let me just write this down. What if you have a case which is AB and AC? Well, you know for a fact that B comes before C, which is right, but where does A come? Does A come before after C, or does it come before B? How do we get that value out? Um, and that's actually really difficult to understand, because if you look at how other things work, you know that A and B don't really have any relations right now. We can't say that A is greater than B or it's less than B, because A is just like standing there. It could be T, it could be whatever, right? So that's actually really difficult to understand. And to maintain all those things, what I'm going to do is I'm going to make sure that I have, for me at least, I want A to be before B and C, because that's just easier for us to understand. But you can ask this question to the interviewer as well. And if they say that, oh, that doesn't matter, well, that's okay. If it doesn't matter, it doesn't matter. You don't really need to worry about it. But we're just adding a new constraint, which is just going to be that, hey, if you don't know the ordering of something, that thing needs to be ordered by the English thing. Just a preset to understanding how we want to move forward. And just to make sure that we are all on this page, we are going to just create an all values dictionary, which is just going to be, I'm going to make this an order dictionary, to be honest, just because I want the ordering to be preserved inside the dictionary, and I'm not ready to show whether that thing is going to be preserved or not. Hopefully it should be, but let's just not take any chances. And all values is just going to contain whatever values have actually been pushed inside, whatever characters really exist inside um, this entire thing. So that's really important for us. So let's just go ahead and update that. So you can do this. You don't really need to do this the way I'm doing it. You could just do a join on all the values inside the word and just convert it into a set. I'm just doing this just so that we don't get any boomerangs coming to us, you know. So let's just do an iteration for all the words and for all the characters in the word, and let's just do if ch in all values, actually if ch is not in all values, then we need to insert it. So let's just add it, and let's just give it a value of true. It doesn't really matter what we're giving as the value, to be honest, but let's just give it that. So that's out of the way. Let's forget about all values for a second. Let's just think about graph and end degree for now. And we're going to be moving in the same way we usually move with our normal approach. The end degree, again, if you're getting confused with it, is just going to maintain a count of whether something comes before or not. That's basically it. So let's just go ahead and code that thing out. So what we need to do is we need to do an iteration for all the words, but we need to do it pair by pair. So keeping that in mind, let's just do a simple for loop with the ith index with range of length of words -1. This will allow me to get the next word as well. So if I do word 1, which is going to be equal to words I can do word 2, which is just going to be words I plus 1. So basically a pair. Again, a lot of different ways of doing this. You can do it whichever way that you want. I just want 2 pairs. So now what I want to do is I want to get the characters out. So I want to do the comparison between the characters. So what I'm just going to do is I'm just going to ch1 comma ch2 and I'm going to zip these two together. So if you're not familiar with zips, that's basically it sort of updates or sort of like meshes together or merges together two lists or two strings and picks them out one by one by indexing. So over here we would have character 1, which is going to belong to word 1, and character 2, which is going to belong to word 2. And it's going to go W with this, then the index is going to go forward, then it's going to be R versus R and T versus F. That's basically it. So keeping that in mind, if ch1 is not equal to ch2, because that's what we want when wrt and wrf and t is not equal to f, that's when we want to perform all our operations. So the first operation is just going to be that we have to update the graph as well. So we're going to say graph ch1, and we're going to add ch2 to this. So all we're doing is we're saying that the node is going to be ch1, which is going to be t in our case over here, and it's going to point to f. And that's being represented as a key value pair where t is the key and f is one of the elements inside our set. So we just to add ch2. That's basically it. The int degree over here is a smart thing that we're doing. So the int degree is going to help us understand whether something can be processed or not. So if I update this as 1, we would have f with the value of 1. And when we have that as a value of 1, we can sort of put a check which can say that if the value is not equal to 0, that thing cannot be processed. So that's basically the idea and the intuition behind all of this. So you're maintaining that value and then sort of moving forward with it. So right now, let's just do a quick print of, let's not do of this thing, but let's do it of the graph to understand how the graph is looking. We should at least have some formations, and we can see that T has F, W has E, R has T, E has R. Awesome. And all of these values which are over here, they would probably just be 1. We don't really need to worry about that right now. So as of now, we've sort of built out a graph, which is pretty simple to do, but now comes the algorithmic part of this thing. So remember that we've used the end degree formulation, and behind end degree, the only thing that we need to take care of is the fact that if something is 0, that means that thing can be processed. If it's not 0, well, it cannot be processed. It's as simple as that. So in our case, let's just do a quick check on what in degree is looking like. So we'll see a bunch of values, to be honest, and some of them we don't really care about. But for us, you can see W is 0, R is 1, which means it cannot be processed, E is 1, and so on and so forth. So we can't process those things before we process the main thing. Pretty important to know, but let's move on from that. So while we're keeping that thing in mind, we can actually fetch out the values which are 0, and those things should belong to the graph as well. So let's just quickly do that. So we can say for k in and v inside in degree, and I'm going to return items because remember this is a dictionary. So getting the key value pairs of the in degree, what we're going to do is we're going to check whether that key actually exists inside the graph. So we can do k in graph, and if it exists inside the graph, that's cool, but it also needs to have a value of 0. If that is the case, then we can push it to a queue. So let's just make a quick list, which is going to function as a queue for us. You can use a deck, you can use the queue, whatever you want. I'm just going to use a list just to make things less complicated for now. So you have queue which has been appended, and if you look at queue right now, the cool part is going to be that from this logic, from the in degree, we've sort of iterated through everything. But with this check, which is k in graph and v equal to 0, we would only have w, which is we're not going to have a, b, c, d because they don't exist. We're just going to have w inside this thing, which is pretty awesome. And using that logic, we can actually just do a quick BFS to get the values out. And you know for a fact I've been talking a lot about BFS before, um, but that's going to be the main idea behind this thing. I'm also going to create a list which is just going to be called result, and at the end I'm just going to join everything, convert it into a string because that's the expected output. Cool. So all we need to do is we need to do a quick BFS. So we're going to do while q, and we're going to keep on popping out the first value of the q as sort of moving forward. Pretty simplistic, but let's move on from that. So basically the idea behind that is just to node q.pop of 0, which is going to pop out the first value inside the queue. Now since we've popped that value, we need to just do a quick check, and I'm just going to do it just for safety's sake, even though that it's not required. I'm just going to do it, just going to say, hey, if node is not in all values, I'm just going to do continue forward with this entire operation. Um, this thing should really not happen, but I'm just doing this for safety checks. And let's just move on from that. So after you do a pop, the first thing that you need to do is you need to append this thing to your result. So let's just go ahead and do that. And appending to the result is actually really important because whatever is going to come to the queue is going to have an in degree of 0. And whenever it's of an in degree of 0, you can basically push it. That's basically the idea behind this thing. Now since we have the node and we have the values that it's pointing to, because do note that the graph was actually maintaining that particular structure, what we can do is we can get all the edges out. So we can say for edges, and edges is sort of a wrong word, I'm just going to call neighbors instead. So get the neighbors for all the values which belong to node, and we keep getting all the values out. So the first thing that we want to do is, since if you look at it, if something has been processed, that means the next values get the ability to get processed as well. But in order for them to get processed, since they are a numeric value, we know for a fact that they need to be equal to 0. So let's just look at in degree for a second, and let's just update this value of the neighboring value to be equal to be decremented by the value of 1. Pretty straightforward, and let's just do a quick check which can say that, hey, if in degree neighbor is equal to 0, which means that this is actually 0, we can append this to the queue. So append neighbor to the queue, and that's basically it. Um, so what's going to happen here, if you didn't get the idea behind this thing, in degree was again our ability to maintain where something can be processed. If we have a list for example, let me just draw this thing out, which has w, like w points to t, which is fine. Um, it's valid, but also q points to t, which would basically indicate that t cannot be processed before w, but it cannot be processed before q either. Um, so these two things need to be processed way before we can come to t. So if you look at that, if this structure is actually followed, our in degree for t is going to be equal to 2. And if it's not going to hit, after we do the processing for w, it's not going to hit 0. It's going to hit only 1. So it's going to be like, hey, you can remove this particular guy, this dependency has gone away. And now we have t, q. Now q also needs, that dependency also needs to go away for t to get processed. Since I'm talking so much about dependencies, one of the variations of this problem is actually something that you would have actually seen a lot, which is used by I think it's inside Maven projects whenever you have a pom.xml, and wherever you have dependencies which are like depending on a lot of things, all these things need to be resolved, and this is one of the main algorithms which is actually used behind the structure to evaluate whether something can be processed before you move forward. Um, a little good to know thing, but yeah, let's just move on. Um, to be honest with you, I feel like we are really done with the solution. You can stop this solution for now and just run this test, and hopefully this should run fine. And you do see that everything's running fine, which is awesome. You can also sort of go ahead and use one of the other things that we are talking about, the all values thing, which was like, what exactly was that, right? With all values, there might be cases where you have stuff like um, XYZ, where XYZ are all the values that are inside, but you only have dependencies with X and Y. You don't know where Z actually goes. So keeping that thing into perspective, let's just quickly code something out which can handle those things as well. So, so again, what I'm trying to say is, let me just put that as a test case as well, so that everybody's on the same page. So you have xy, sorry, let's do zy and zx. Yeah, so let's just run this. You can see by our formulations right now, only x and y are the ones which are going to be processed, and that's what the output is. But if the interviewer says, hey, where does z go exactly? Well, you need to update that somewhere. Since the expectation over here is that the z value should go at the very end, because that's just something that we follow inside our English language. This is build that thing out. So what I'm going to do is we're going to do for val in all values. So basically get all the values which are coming in. And if val is not inside the result, we need to append it somewhere inside the result, right? Pretty straightforward. Where exactly do we store it? That's more important. And we're just going to create a small method. So we're going to say find small list, which is going to be a simple method for us, which is going to take in the present list, and also the value that we're checking. And all this thing is going to do for us is just going to return an index for us. So we're going to do for index ch in enumerate of present list. And all we're going to check is whether ch is greater than the value which has been passed in as a parameter, and if it is greater, then we return the index, and otherwise we return the length of the present list. So what exactly is happening over here? Well, it's pretty straightforward. All you're doing is inside the present list, which is y and x for now, you're going to check each and every single value. And if the value is greater than the value which has been passed in the val, well, in that case, our val should be pushed in before that particular ch. Just because, well, we don't know where it goes, so we're just going to say it should follow the index paradigm. Well, if that's the case, then ch, whenever that's greater than value, we can just return the index and sort of move forward with it. And since that index is being returned, we can use that inside a function which most of you would already be aware of, which is called insert. So if you don't know about it, so we know for a fact that result.append works. It appends into the last most item inside your list, but there's also something called as insert, which is a function inside a list, which can take in an index value and the value that you want like input inside of it. So we look at all these things, we say that, hey, yx is actually less than z in our case. So that will return the end condition when these conditions are not followed through. And we say that just return the present list. Beauty of the insert is that it does work with length of this thing. So if you give a length of 2 and, sorry, length of 3 or something like that, it would actually update it over there and sort of move forward with that thing. So that sort of gets resolved for us. So let's just go ahead and run this code, and hopefully this should run fine. Um, it takes a little bit of time with hidden code, but yeah. Okay, cool, awesome. So you can see that's running fine. Let's just talk a little bit about the previous case as well to check whether that thing does not break. So I'm just gonna go ahead and copy this thing and bring this back up and run the previous case. Hopefully that should run fine. And it does run fine, and that's basically the entire ideology behind how you would want to try to solve the alien dictionary problem. This entire video was a little long because I want to help you gain an intuition behind how you would sort of work around with these things. The end degree is, so once you sort of resolve the fact that this is a graph problem because of all the dependencies which are coming in, you can see that you need a way to also resolve those graph dependencies as well. You can't push everything inside the same data structure, even though you sort of can, but you shouldn't. Uh, if you do that, then well, you need to worry about the in-degree stuff as well. You could sort of take care of this thing and just remove this thing and say that, hey, once I'm done with the graph, just remove it, remove the node altogether if the node has been processed. But that would also work. You would just have to check each and every single node afterwards just to see whether that node has some pointer to it. Um, Again, there are like multiple ways of solving this problem, but I like the in-degree method just because you have a lot more control and flexibility to understand what exactly is the value as you're sort of moving forward with your entire approach. And all we are doing is we sort of keep on updating the in-degree whenever there is a dependency on it. So you can call it the dependency tracker if you want, but all it's doing is just maintaining the number of edges which are pointing to that particular node in a way. And if you keep on resolving those nodes, you keep on removing that particular edge away from that node. So again, like it's the exact same example which I was talking about, but overall that's the idea behind this thing. And I promised you I will tell you the algorithm behind this thing at the end. And the name of this algorithm is actually it has a lot of semblance with topological sorting. So if you didn't know what that was, well, now you know. It's the same exact logic. You do the in-degree calculations, you do the edges calculations, and you keep on removing the edges as you keep on doing the processing, and you're basically done. And again, this problem has a lot of variations to it. So whenever you have some problem like this where you want to understand what goes before something and it's getting difficult, probably you want to think about a graph approach. I think there's another problem on late code which is called core scheduler or something like that, which sort of revolves around the same paradigm as well. And that's basically it. So if you did like this video, do give a like, and if you do have any comments, if you do have any suggestions, do give it in the comment section below. I would love to hear from you. We have discussion over here, and whenever somebody gives a response, I try to respond to it as soon as I can. So again, if you've already subscribed to this channel, thank you so much. You're awesome, we all know it, and have an awesome day. Thank you so much.